means our reference is somewhere there as 0. So we have the phase on A, phase on B, and C, defined by those boundaries. So similar to what was done on the hollow structure, if you evaluate the field here, you realize that the E field, depending on where you have inserted your exciting probe, that the E field can be defined by an equation that is in the X direction, Y direction, and Z direction. And so you can define the propagating field, Ez, as the amplitude, some amplitude, times the sine of the mode M, pi x over A, times sine of the mode N, pi y over B, times cosine of P, pi z over C. So in this case, what is the mode of this resonator? Remember, for the hollow structures, we have Mn modes. So for the resonator, it becomes MNP. MNP. And here we will take C to be more than A, but we had agreed that for our designs, A is more than B. The hollow structure. So in this case, it will be C more than A, that is more than B. Okay. So this is how the propagation is defined within that structure. Because it is close-ended, what would happen? It won't be there. What it means is that you will have your propagation towards the end, or towards Z. But what happens at the end? There's a reflection back, which is forming a standing wave. So let's just take an example of one oscillation. So you have a standing wave within the waveguide, which is now what we call the resonator. Now, in this case, remember, you continue to inject. So you can say this one is the one that is incoming, incident, and the other one is reflected. The red one keeps on growing because it's a continuous injection. It's like a generator. So what would happen is that you will be increasing the amplitude of the standing wave. And energy is going to be stored inside here. Storage will take place, which you need to convert into some use. All right? Otherwise, then there must be, normally for energy flow, there must be a gradient between the source and the load. So there must be a load there for you, for that propagation to take place. So now we can write our phase constant. Remember, beta, we know beta is defined in many ways. Say phase constant, 2 pi over lambda. Or if you add f there and f down, what will you have? You can see it's defined as omega over c. So beta is now defined through that mode of propagation as this value here. And now we can write the resonant frequency, because we know omega is 2 pi f. So fr, we can redefine now fr to be, because we know beta is omega over c. So omega is equal to beta times c. So it's beta times c, but c is 1 over root of this product, mu epsilon. So you can see, so we have omega is equal to beta over root of mu epsilon, which is beta times c. And now we can get the resonant frequency as that. Okay, so FR, because we have 2 pi here, and beta is here, so you divide by that equation here, this one and that. So it's FR is equal to omega over 2 pi r, and you have beta in terms of omega, so you get that value. So it means we can now calculate the resonant frequency inside the rectangular, rectangular cavity. But you may have several other modes which could have the same resonant frequency. Okay, different modes, because now you have a different value for A, B, and C. That will remain constant, but you have different values for M, N, P for different modes. So you may realize that your computation of resonant frequency may be the same. You may get the same resonant frequency for different modes. Now, those are the ones that we call degenerate modes. One of you was asking before. So we call that degenerate mode. So different modes may have the same resonant frequency and thus degenerate. But because you can excite the resonant cavities in different ways, you have opportunity to excite from this end, okay, all the 6 faces. So you may not have to work with degenerate modes. Okay, you may actually excite it in different ways, and that may lead to only a single mode to dominate rather than having several ones with different resonant frequency, with the same resonant frequency. So what is important is the quality factor. We have seen that you can store a lot of energy within the cavity. So what is important for us is to determine the quality factor inside that cavity, or probably there's a certain amount of energy that you need to attenuate or retain within the cavity. So what do you do? So you can look at the quality factor in different ways. Remember, the walls of the resonant frequency are made out of materials which could have finite conductivity. So if they have finite conductivity, that conduction will lead to a loss within the cavity. The coupling system in which you are using to excite the signal inside there also may also affect the amount of energy that you store within the cavity. But the dents on the wall as well, the propagation depends also on the path. So the dent on the wall would cause some surface irregularity, and those surface irregularities would probably interfere with the permeability, and that also affects the quality factor. So you should be able to explain what are the reasons why the quality factor may deviate from what is expected, the ideal value. So we need then to explain or define the quality factor for resonant cavity. Okay, so we can use that quality factor to estimate the loss inside a given resonant cavity. So we define a quality factor as 2 pi times the time average energy that is stored within that cavity. Then you divide by the energy loss per cycle of oscillation. Okay. So time average energy stored over the energy loss per cycle of oscillation. So you don't forget about the energy loss per cycle. So it's actually the total amount of energy. So from this definition here, can somebody tell us time average over a certain amount of time that is stored, but you only want to divide by the energy loss only per cycle of oscillation? What indication does that give you about the quality factor? Is it possible for quality factor to be equal to 1? do you think it could be less than 1? Do you think there's a scenario where it is much more than 1? Or is it possible to have a 0 quality factor? Somebody can attempt any that you understand better, or all. Which scenario is realistic from that definition? The time average energy stored cycle of oscillation. Or to ask again, in what scenario do you think Q will be equal to 0? So if we don't have any energy being stored within the cavity, that's when we'll have a 0, Q equal to 0, if there's no energy that is stored. What are the scenarios that can lead to that? Probably you are not exciting any signal inside that cavity, or whatever you're going on is leaking out. If it is equal to 1, it means the energy that is stored is equal to the average energy loss. Okay. If it is less than 1, it means the loss is more than the storage. And if it is much more than 1, then it means it is almost perfect. So the scenario that we desire is that. That's the scenario that is desired, that our quality factor should be much more than 1. So it's 2 pi times the energy that is stored over the energy loss per cycle of oscillation. So it means energy loss per cycle of oscillation is the power times the time. And this is the period of oscillation. This is the power loss times the time will give you the energy. This is the energy stored. You can have energy stored at omega E over P loss times time, 2 pi F. So you may find in other texts, what would you have? You will have, this can be written as energy stored over power loss, but times 2 pi. Now you remove this T here, which is 1 over F, which is omega. Energy storage over power loss. So either way. So T is the period of oscillation, time average power loss is PL, and W there is the time average energy stored. To have a very high Q compared if we were to use the RLC that would radiate the due to the low. At high frequency, there will be a very small skin depth. So most of the energy will be flowing by the surface where we lose them due to radiation in RLC. So that's why we use this cavity. So through derivations, remember we said here we are concerned about application, though we can look at how to determine the quality factor for different modes. So here modes are M and P. So we can start with TE101. The rest of the modes you can read from the text. So TE101 can be defined as the dimensions of that cavity divided by the skin depth. So this last time we might have talked, I don't know whether it's this class. Did we talk about a skin depth? Can somebody define what a skin depth is? Because it's very important for us in this semester. What is a skin depth? because depth is distance. So why that? Why do we call it skin depth or skin distance? What happens at that distance?
%63.
63? % of the energy? In the skin depth. 60% of that amplitude of that signal is defined within the skin depth. So you have only 37% going towards the core. So it's from the surface. So you must state it's from surface. So that skin depth is defined as, it depends on the frequency, permeability, and conductivity. Okay. And also, do you think the skin depth depends on the permittivity as well? Because we just have pi f mu and conductivity. I don't know whether somebody had something. Somebody raised a hand. Tony? The distance to E is -1 for a signal. Yes, that's correct, Samuel. Then attenuated. Okay. Tony, did you raise your hand?
I don't think.
It was earlier. I hope you guys can hear me. I realize my speaker was too low. Okay, fine. So we can proceed. So do you think the skin depth also depends on the permittivity of the material? Somebody wants to try? Do you think the skin depth also depends on the permittivity? Okay, you can hold on to that question. Then later, try to see if you can remember or try to see the insight. Okay, so causes of low quality factor, we've talked about irregularities could cause some increase in the permeability and hence the skin depth. Then the conductivity of the cavity wall would also influence the quality factor. So you need to check, what does the conductivity do to the quality factor? Conductivity is inversely proportional to this. So higher conductivity, does it increase the quality factor or lowers it? Looking at equation 21 and 22. What does the high conductivity of the cavity wall do to the quality factor? Does it increase it or lower it? So get
Increases.
it increases. All right, you can see it increases. Because if you put this question 22 into 21, this will go up. It will be in the numerator. So it's also the resonant frequency and permeability. Okay. Coupling system, whether it's aperture or loop, definitely also the efficiency of that system would also affect the quality factor. So those are the causes of low quality factor in resonant cavities. Now let's see if we can get some resonant frequencies for a cavity factor. Here we are only using TE101, where M is 1, N is 0, and P is 1. Do you think there's a case where we could have a TE mode? 100 we know is possible for hollow. Do you think it is possible to have TE100 for a cavity? Or I could ask this way. Do you think this is the same as TE, the dominant one, in a waveguide, TEMN 10 and TE100 in the cavity? Do you think they are similar? So the question here is, when we have P is equal to 0, it means then that end is also open, isn't it? So it's not closed, then it's no longer cavity. It's just a hollow structure. Okay? So in that case, is similar to that cavity would be looking like a hollow waveguide. So that's not what we are looking at. We are looking at a closed. Okay, those are just for insights for you to understand what you're doing. So let's have an example where you have a C more than B and more than A in that order. So an airfield, this is airfield, so you have to take note when we say airfield and maybe filled with some material inside the cavity. So an airfield resonant cavity has dimensions ABC, which is 5, 4, 10, and made of a material of conductivity. You're supposed to determine the 5 lowest order modes. Okay. Then determine the quality factor for TE101 mode. Then now we fill it with a non-lossy material with a relative permittivity of 2. And you're supposed to tell us whether the quality factor reduces or increases. And that's why I was asking you whether you think that the permittivity affects the skin depth. Because here we have permittivity increasing there for that material. Okay, so we'll see that. Does it reduce or increase the quality factor? Okay, what is the new value of the resonant frequency when you fill it with a material? And what is the new value of Q, TE101, when you fill it up? So for us to determine the modes, we are going to do the resonant frequency for several modes. Okay. And we have said when P is equal to 0, then we are not really talking about the cavity that we have. So it means you can do what frequencies? Start from? You calculate FR101. And do what? Maybe 01 or 011, right? You can do what? 1, 0, 2. So you increase P to 2. You can do 1, 1, 1, 1, 1. and check, form the lowest order modes. So using this formula, can somebody determine the quality factor for TE101? You have the dimensions and you have the conductivity. So we want to get the resonant frequency first here, because that's what we're trying to answer. So can somebody calculate the FRTE 101? What do you get? And we're using this formula. F, you should know it, but let me just open the page. So you have, maybe I can rewrite it. Let me just rewrite it. Sorry. So you have C over, which formula do you want to use? It depends on which one is easier for you. So you have FR can use C over 2 of M over A squared N over B squared plus B over C squared. And we are requesting for TE101. Can somebody compute that? Let us know what you obtain. You're looking for this first one. So M is 1, A is 5 centimeters, so change this to meters, square it, then B equal to 0. The second term goes 0. P is equal to 1, and C 10 centimeters. What is FR? 101. Is there anyone computing it?
.354 gigahertz.
3.35 gig. Okay. Can somebody compute TE? I think what I needed to explain in this bracket here is that we cannot have a cavity, not actually the mode, not the what do we call it? The half wave number of half waves that we see on those fields, what I meant here is that you cannot have a cavity with C equal to 0. You cannot have a cavity with C equal to 0 because that becomes just a hollow waveguide, not P equal to 0, but C equal to 0. So you have 3.35 gigahertz. Can somebody get TE012? We want FR for 012. So it is C that we can't have that as a cavity. If C is equal to 0, it means it's open. But these half wave variations can still exist depending on how you excite the wave. So FR TE012, somebody? What do you get?
4.8 gigahertz.
The answer is
4.8 gig. Then somebody, can you do TM110? So FR 110. What do you get?
getting 4.8 gigahertz.
So you also get 4.8 gig. So is somebody able to see degenerate modes? Which modes they are degenerate?
TA012 and TM110.
110. Okay. So you can see you can excite them differently. So if you excite in the TM, then you will just have one mode. If you excite in the T, you just have another mode. But you see the resonant frequencies are the same. Okay. So I agree with those values of 4.8, 4.8 for 110 and 012. What about the quality factor? Can somebody compute the quality factor? We say the quality factor is Q. We want just TE101. You will get used to this, you'll master them. It's A squared plus B squared times ABC. The C that is missing. What is that? This is A, I think I'm wrong. A plus C. C squared ABC, then over the skin depth times. Now B, which is missing there, you have 2B into the cubes. A plus C squared. We already have B. C cubed plus AC into squares, A squared plus A squared. Where the skin depth is? And you've been given that, all that's. So you have, we are looking for QTE101. You have FR101 as 3.3 gig. You have the conductivity as 5.7, 85 times 10 raised to 7. You have pi, you have mu, 4 pi times
10 raised to power 7.
10 raised to power 7. And mu naught is that. So because mu r is 1, so we just have that as mu. So can you compute? You can compute the skin depth, you let us know, and then compute the quality factor. Do you get something around that, whatever is showing there, 14,000? But give us the skin depth first.
Could you only scroll up to the so that I can see the conductivity?
You want to see the
conductivity?
conductivity here? Are you able to see it? The one I'm surrendering now in red. This value here. Are you able to see it?
Okay. I think my screen is lagging a bit. My screen is lagging.
Okay.
Let me reload.
Are you able to see it now? So maybe I put it smaller or bigger. I'm not sure what you're saying. So anyone skin depth? Because already the conductivity and that will cancel out, but F is in gigahertz. So I'm expecting something in the micro dimension because the permeability and that conductivity will cancel out, but F is in gig. Something to do with micros.
Yes, it's 1.14
micrometers. So this is correct. All right. Okay, good. Thank you. Yeah. So anyway, that is arithmetic. It's not our big issue here. So factor, you should get something about 14,000. What I wanted to show is that you can see the amount of energy that is stored is so much compared to what is lost. Okay. Because you're continuously injecting energy into this cavity and it's not coming out. Just staying there.
Excuse me, sir.
Yes.
Okay. I had a clarification concerning the number of half variations that you are using.
Yes.
Normally, for analysis of waveguides, we were using M and N as the half variations. But then
Yeah.
when it comes to the cavity resonators, we are including P. I
Yes.
wanted to know the significance of using P and what happens when you vary P from 1.
Yeah. Means is that you have some variations on the. Remember, when you have a hollow, how many surfaces do you have? A hollow waveguide, how many surfaces do you have? Whoever asked that question, I didn't see your name. When you have a hollow structure, how many surfaces do you have in a cube, or a cuboid or a cube? You have 4, isn't it?
Yes, yes.
You have 4, so just you have 4, so it means half of them will be just M and N. But when you close the ends, of that hollow structure, so you are going to have 2 additional surfaces, isn't it? So the energy that is the variation that is going to happen on those 2 extra surfaces is what we note as P. The half cycle variations on those other surfaces is what we note as P. So if you are able to excite more variations of energy, it means then you are able to send in more energy within the same time period. So you can see if there are more variations in terms of P, when P is 0, means no variation, 1, 2, 3. So if you do that, maintaining everything else, what happens to the quality factor? Quality factor goes up according to those values, isn't it? So it's just like you are able to multiplex signals within the same time slot. So if you do that, what are you doing? Basically, you are increasing the energy that you are able to send in. So the issue should be, how do you make sure that you have, that is what is difficult. How do you excite it? But so long as you excite it, you can see from the equation, it will increase the quality factor. Are you answered? 2 is the extra surface. Number 1 is the extra surface that you had.
Yes, yes.
Okay, thank you very much. So you add on this on the hollow structure, and then now the equation will tell you what happens. All right, good. So if that's clarified, that's good. So example 2, you're supposed to show that for a cubical cavity resonator, then the cutoff frequency is given as C over 2A. Now that one is easy. Over root 2A. This you can show from that equation that we have given, because this is now a cubical. Cubical just means then A, cubical just means A is equal to B is equal to C. So you can reduce this formula and show that. Then show that for a cubical cavity resonator, the quality factor is given as, very simple, just A, because the sides are equal. A is equal to B is equal to C. So just A over 3 times delta, which is the skin depth. Again, in that case, it's easy to show. Now you're supposed to consider an airfield. Now this is airfield, cubical cavity. So this is a cube designed to resonate in TE101 at 10 gigahertz, and the walls have conductivity of 6.14 times 10 raised to 7. Mu is given as mu naught, and you're supposed to determine the quality factor. So the only difference from the example 1 is now this is cubical. So it's very easy, but I don't like you mastering it like that. If you know how to do the one for cuboid, then it's easier to reduce it to the cubical one. But if your master is good enough, so you can easily calculate that. So you have A. So consider cubical that with the plate there. Then determine the quality factor. So you just have, A is given as 2.12. You can calculate the skin depth. You have the frequency. You have the conductivity. You have pi. You have mu, permeability, which is 4 pi times 10 raised to negative 7. So you can calculate the quality factor and think almost 11,000. Then this should be modified. So you can have, okay, maybe this is testing something else. This is a cubical. So it's made up of a material with conductivity is given 5.8, operated at 15 gig. You're supposed to determine the quality factor. Then the bandwidth if operated in the dominant mode. And then the cavity now has a complex dielectric constant. So complex dielectric constant could be caused due to some variation in humidity or air temperature. You have some changing dielectric constant because of humidity. So in that case, it means that the effect of that dielectric constant at the boundary where air is less dense or more dense than the other would cause some complex permittivity, and that will affect the. So in the presence of a dielectric loss of a complex nature, we would have to calculate the dielectric loss, quality factor of that dielectric loss. So which will be, if you have the complex permittivity, so you get the quality factor, which is synonymous to the energy storage and the loss. So you have the effect of this is like complex power. Okay. So what the effect is that it would look like you have that.
Excuse me, sir. I have a class beginning now.
Right. So we just finished this. Thank you. So you have QD, the dielectric loss, epsilon 1 is now like P, whatever is coming in, and this is returned. So it's like a loss. So you have to calculate the quality factor in terms of that permittivity. And now you combine it with the loss in the cavity. So you have the one in the cavity is QC, which is computed usually, the one we have just done previously. And then you have this dielectric loss. So the sum of the two will give you the complex quality factor. So complex quality factor will be the product of the loss in the dielectric, so long as you have that, and product of that loss in the dielectric and the one in the cavity over the sum. The bandwidth you calculate as the resonant frequency over that quality factor. Okay. So bandwidth of that cubical resonator will be FR over the quality factor, the complex quality factor, or the total quality factor. So that's why I wanted us to reach. So from next Tuesday, we'll have the first group presenting. I don't know which, okay, I have not checked the groups and the topics. So let's prepare. It doesn't always have to go group 1, group 2, group 3. It depends on how you group them. I'll have a look. So you can send in your attendance through the chat. Or it's a physical class for the telecoms, so you have to go. What you can always do is that go to that class and maybe have my class from there.